In this video, we're going to be talking about condensers and subcooling. Now, condensers, we know from our refrigeration cycle conversation, is the part of the refrigeration system which receives the high temperature, high pressure vapor from the compressor, removes the heat from the refrigerant until it turns back to a liquid state. Now, the condenser actually does three functions. It de-superheats, which is the first part of the function. Top couple coils of the condenser de-superheat. What that means is lowers the sensible heat, that's the heat you can measure, to the point where the change of state, and change of state just means from a gas to a liquid in this case, takes place. Then the center portion of the condenser, roughly, takes the vapor refrigerant, removes the appropriate BTUs to equal the latent heat content, and changes that refrigerant to a liquid. Okay, now let's just say it's 125 degree gas, sensible heat wise. It's still going to be 125 degree liquid. All we're doing is removing the latent heat. Okay, that's the heat of vaporization, the boiling point. Okay, it's removing that liquid heat to put it into a liquid state. Then finally, in the last couple passes of the condenser will do what we call subcooling. Now, subcooling again is sensible heat removal. So it takes the liquid refrigerant from that 125 degrees that I just used as an example and cools it could be 30 degrees lower before it goes into the liquid line. Okay, and that's subcooling. So our condensers de-superheat, condense, and subcool. The condensers have to be larger than the evaporator. They should be able to hold 100% of the charge of the system without a receiver. Now, in refrigeration, we have a tendency to cheat a little bit on this, and we put a receiver just for safety's sake. I don't want liquid refrigerant backing up to the compressor. Condensers have, again, they remove heat via the heat of evaporation, that's the heat absorbed from the evaporator, and the heat of compression, that's the heat produced by the compression process. Remember, whenever I press something together, whenever I compress something, whenever I work with a material, we're producing heat. The compressor also produces heat that has to be removed by the condenser because the refrigerant cools the compressor motor windings. So that all produces heat as well. There are a couple things that affect the capacity of the condenser. That's how much heat I can remove. First is the surface area. That's the physical contact area of the condenser to whatever I'm using to remove that heat. That could be air or water. And then we also have to worry about the temperature difference between the air and the water and the condenser material, okay? So let's say my refrigeration gas is doing my change of state at about 125 degrees. That's sensible heat. I still have to remove a bunch of latent heat. So if I have a 90 degree day, which is the 30 to 35 degree difference, my condenser is going to be somewhat efficient. That's about the right point. But if I go up to a 100 degree day in the sun, okay, I'm going to have a lower temperature difference, and therefore my condenser is going to have to work harder to remove that heat. So the larger the temperature difference between the refrigerant temperature and the outside air or water, the quicker heat is going to be removed. Now, when we get too far of a difference, we start having a problem where we have to worry about low ambient temperatures and stuff like that because of pressures. But again, the larger the temperature difference, the more heat is going to be removed from the condenser. Okay, we also have the velocity of the gas going through the condenser. Now, velocity is basically speed. Okay, so the faster the refrigerant flows through the condenser, the better the heat transfer, the greater the capacity. We also have the material the condenser is made of. Aluminum passes heat much easier than steel. Aluminum passes heat much easier than copper does, but aluminum breaks down easier. So there's some trade-offs there. And then we also have the cleanliness of the surface area. Dirty condensers, condensers that are full of leaves, dirt, mixes of flour, water, and other stuff you find in restaurant kitchens, grease, okay, do not transfer heat very well. So there's only a couple of these things that you as the technician can actually control. The biggest one is the cleanliness of the surface area. Dirty condensers do not transfer heat, so the cleaner the better. Dirt is an insulator. Large condensers, like the ones you see on the larger central air conditioning systems, you know, the big ones that a human could possibly crawl inside of, okay, they have a good cooling difference between the refrigerant and the cooling medium. The result is a low discharge pressure and good subcooling. Small condensers, like the type that you find on the refrigeration trainers and the restaurant, the reach-in units, and the condensers that are found like in the bottom of soda machines and other refrigerators and stuff like that, have very small condensers, okay? Very small area for heat exchange. Little temperature differences. The result is a pretty high discharge pressure and very little subcooling. So the condenser side has to do with subcooling. Now I'm going to talk more about subcooling, but that's basically the difference between my condensing temperature, that's your pressure of your high side gauge, converted to a temperature, and the temperature you take on the liquid line. That's subcooling. Dirty condensers, regardless of what size condenser, has a little temperature difference between the incoming and outgoing refrigerant. The result, again, is a very high discharge pressure and very little subcooling, which is not a good thing. Condenser capacity. The end result of a condenser that is small or dirty. Overheating of the compressor, boiling of the oil in the compressor, and in turn, compressor failure. Okay, remember I told you in a prior lesson that you have the ability to cause a compressor to fail or to prevent a compressor failure. The biggest issue is dirty condensers. Okay, dirt plays a big issue. We have two types of condensers, two overall categories. We have air-cooled and water-cooled. Air-cooled is what you're finding on most of your residential air conditioning, most of your restaurant equipment these days, most of the smaller type systems, okay, until you get to big commercial high-end systems. Okay, it uses air to cool the condenser coil. Okay, in other words, we have fans that pull air across or through the coils, and there's fins on the coils to expand the surface area. Water-cooled condensers, they are uses water to cool the condenser. They're found in large commercial, ice machines, and some geothermal applications. The water could be recirculated, sometimes it isn't. Okay, air-cooled condensers now have a couple small categories that go under it. Natural convection. Okay, it transfers the heat to the surrounding area by means of natural airflow. There are no fans on these systems. Could be a wire static. Okay, it's constructed of steel tubing interlaced with wires, mounted on the back of the unit. It's cooled by the ambient air. Basically, hot air rises. So as the air heats up, it moves across the condenser coil, pulls the heat along with it, and cool air comes in and replaces it. If you look at the back of some of the older refrigerators and older freezers, you see these. Okay, it's a condenser coil that's on the back, and it's just cooled by ambient air. We also have what's called a plate static or a warm wall condenser. Again, no fan. The tubing is in contact with the outer wall of the unit. Basically, it's mounted between the inner and outer walls of the unit. They use the same principle as radiant heat to cool. The walls get hot, and hot air rises, cool air comes in contact with the wall of the unit. And the advantage of this type is that it allows the unit to go flush to the back wall. Okay, and no sidewall heaters are needed to prevent the frost. The main disadvantage is that leaks are hard to find and very costly to repair. You can't easily find leaks with these. Now, what you see these a lot of times in is freezers, domestic freezers, okay? If you look at a freezer and feel the wall, feel the outside side walls of it when it's running, and if it feels warm, that's because the condenser is actually built into the wall of that freezer. Now, air-cooled condensers, the most frequent one is forced draft condensers. We use a fan to move the air through the coils. The fins are connected to the condenser tubes to provide more surface area for heat transfer. This is what you're going to find on most residential commercial air conditioning and most freezers, commercial equipment, most refrigeration equipment uses forced draft condensers. We use a fan. Okay, condenser fan motor with a blade to pull the air through the coil. Now, if you look at the coils, you don't just have a copper coil or aluminum coil. We have fins that have been mounted on that. All that does is increase the surface area, make more area available for heat transfer. The normal temperature between the condensing point of the refrigerant and the ambient air is between 20 and 30 degrees. Now, I have actually seen this referred to as 30 to 35 degrees, depending on the different books you read. But it's a rule of thumb. If you can get 30-degree difference between the outside air temperature or the air around the condenser and the refrigerant condensing point as your high side gauge converted to a temperature, you're in the perfect realm of things, unless the manufacturer says something different. The condensing point of the refrigerant is found by converting the pressure in the condenser to temperature. Subcooling takes place in the last few passes of the condenser. To measure subcooling, use the condensing point, that's your high side gauge converted to temperature, and subtract the temperature of the refrigerant leaving the condenser. Okay, now, the temperature of the refrigerant leaving the condenser is measured by putting a clamp on temperature probe or taping your temperature probe to the liquid line as it leaves the condenser. The temperature of the refrigerant is on the outlet of the condenser. Subtract the two. If the condenser has a fan that enhances airflow, it is a forced draft condenser. Okay, window air conditioners, refrigeration systems, split systems, that's where your outside unit has your condenser and your inside unit is connected by a line set. And all of our shop condensers that are found in the shop equipment has air-cooled condensers. Water-cooled condensers were actually developed first, and we're starting to see a little bit of return to them as well. Water-cooled condensers are more efficient than air-cooled condensers as long as we recirculate the water. It's the same principle as an air-cooled condenser, but water is used to extract the heat instead of the air. We circulate refrigerant either through a chamber that has water around it or through pipes that are in contact with water, and we use the water to extract the heat out of the system. Water-cooled condensers come in different types, just like air-cooled condensers, but there are different purposes and different troubleshooting. We have tube and tube, shell and coil, shell and tube. Okay? The most frequent one you're going to see in equipment that is not high-grade commercial equipment is your tube and tube. It's made by putting one pipe inside another larger diameter tube. Okay, I think on a few of the shop benches, there might be some of these that have been built. The tubes are wrapped in a circle to save space. The refrigerant is in the outer tube, and the water is in the inner tube. Now, the refrigerant and water obviously can never mix, so leaks are important here. The heat is transferred from the refrigerant to the water through the walls of that inner tube. This style is frequently used in ice machines and geothermal heat pumps. The biggest issue with these is that mineral deposits will eventually build up in these condensers and they need to be treated or cleaned. As minerals build up, it prevents water circulation. The next type is the shell and tube. Okay, there's a shell or a container that contains the refrigerant. The tube running through the refrigerants with a high rate of water. The heat exchanges from the refrigerant to the water, condenses to a liquid, and comes out of the bottom in a liquid line. This is known as a water box. Okay, so again, we have a shell or just a big box. We put the hot gas refrigerant into it. We have the liquid line coming out of the bottom, just sort of like a drain. There's water that is in tubes that run through this. So as the refrigerant condenses by exchanging the heat to the water, the liquid refrigerant by gravity flows to the bottom of the chamber and flows out in the liquid line because of the pressure behind it. Shell and tube condensers are known as water boxes a lot of times. The end caps of all of these can be removed so that tubes can be brushed out and cleaned to prevent mineral buildup. Again, mineral buildup is a pretty major issue with water-cooled condensers. Water does have minerals in it, and it will eventually start building up on metal and cause blockages. Now, we also have a shell and coil condenser characteristic. It's the same idea as the shell and tube, but a little less expensive. Waterline is coiled down the center. Okay, so we still have the shell with the refrigerant that is flowing around it, vapor at the top, liquid at the bottom flowing out into the liquid line. But instead of having caps that we could pull off the end and brush out the tubes and clean out the tubes with the water, we can't do that with a shell and coil. Okay, it's very hard to clean if minerals build up. It's basically replacing the water coil inside. So the biggest question is, what happens to this water? Okay, so I have cool water coming in the top. It comes in contact with the refrigerant. It pulls the heat out of the refrigerant. Okay, or the refrigerant rejects the heat to the water. Okay, we have to do something with this water to get rid of it. Now, we have one way of doing it. Some systems are called wastewater systems. Water's used once and then wasted. Obviously, this is causing problems in very many communities, especially for people who have to pay for water. The others are called recirculated systems. The water is used to cool the condenser, and then the water is cooled and recirculated. These are the most frequent at this point. So, how do we cool the water? One way is by use of cooling towers. Okay, now cooling tower basically is what it is we take this hot water coming out of our condenser, we take it up into a tower that might be mounted behind a building or up on the roof of a building. We spray it down through just standard air, and we allow the air and the evaporation of the water to pull heat away. But its use is limited by outdoor wet bulb temperature. They require yearly cleaning and consistent water temperature and air movement. Here's the thing. So we all know that evaporation works best in a dry climate. Okay, water evaporates faster if there's lower humidity. If there's extremely high humidity and high temperatures, the water isn't going to evaporate that well because the air already has a lot of humidity in it. So cooling towers work best in a climate that has a relatively low humidity and lower temperatures. Okay, so a cooling tower in Arizona is going to work very, very well because it had 10 and 15% humidity. A cooling tower in New England will work well because of lower temperatures. Still higher humidity, but the temperature makes a difference. A cooling tower in Florida isn't going to work well at all because of the high temperatures and high humidity that's present at most times of the year. Yearly cleaning is required because the water's open to the air, thus algae will build up eventually. Consistent water treatment, again, we want to prevent the algae building up, and air movement is required. Okay, the refrigerant in a water-cooled condenser normally condenses at 10 degrees higher than the leaving water temperature. So if my leaving water temperature is 70 degrees, the refrigerant is condensing at 80 degrees. Convert that to pressure to find whatever pressure you have. A recirculating water system will circulate the water at about 3 gallons of water per minute per ton of refrigerant. So again, 10 degrees higher than the leaving water temperature, and about 3 gallons of water per minute, so 3 GPM per ton of refrigeration. The water regulating valve will regulate the flow of water through the condenser. Okay, the water regulating valve is controlled by the discharge pressure of the compressor. As the load increases, so does the head pressure, and so does the water flow. When we adjust water regulators, we always want to adjust water regulators to the manufacturer's recommended flow rate in gallons per minute. Trust the engineers that built the system. A properly functioning condenser will desuperheat, condense, and subcool the refrigerant. When a condenser is placed in a low temperature environment, like on a restaurant roof in Massachusetts on a negative 10 degree day, we want to use a low ambient, or otherwise known as a fan cycling control, to cycle that condenser fan on and off to maintain the high side or head pressures. Low ambient temperatures seriously affect the temperature of air-cooled condensers. The lower the temperature, once you get below a certain point, the pressures are going to drop in the system. And sooner or later will drop enough that we're not going to get our heat coming off. We're not going to absorb heat properly through the evaporator. Now, subcooling is a temperature of a liquid that is cooled below its condensing temperature. So we have our condensing point. The liquid refrigerant has condensed, moving through the rest of the condenser. There's further cooling going on. That's subcooling. It's a sensible heat removal from the liquid after the change of state has taken place. Subcooling is used to determine if the condenser has the proper level of refrigerant. The complete condensing of refrigerant should occur in the bottom quarter of the condenser. Any heat that is removed after that point is subcooling. The general idea here is that you're using as much of the condenser as possible to do our latent heat change. Okay, we need to have enough of a charge in here so the condenser is relatively full of refrigerant that is being change of state. We don't want to have the entire condenser full of liquid refrigerant though either. So we want to have enough of a spot in the bottom where we have liquid, but not too much liquid and not too little liquid. The greater the subcooling, the more liquid is in that condenser. Subcooling is needed to maintain a proper system balance. Normal subcooling is between 10 to 15 degrees in the older style condensers. We're now seeing this up to 20 to 30 degrees in the newer style. It's very dependent on how efficient the condenser is. Subcooling will also change depending on the type of refrigerant and the application. If subcooling is low and you have high head pressure, you possibly have a dirty condenser. Check condenser fan operation. Look for overcharged conditions. Do you have non-condensables? Okay, did somehow air get into the system? Nitrogen left over from the last time the system was pressure checked. Okay, you possibly have a restriction before the evaporator coil. If the subcooling is high, look for a low charge. Okay, sometimes could be overcharged a little, but most often low charge. Check the compressor amps. If lower than RLA rating, then you have a low charge. Subcooling can be accomplished by placing the liquid line and the suction line in direct contact with each other. You'll sometimes see the liquid and the suction lines welded together or brazed together in small or low temperature units. The higher the subcooling is, the more efficient the system. The liquid in the liquid line is cooled below the refrigerant condensing temperature, and the suction line would be warmed slightly to boil any refrigerant that's left over before entering the compressor. It's sort of a win-win situation. By the suction line being cool, we're lowering the temperature of the liquid, and we're also boiling off any remaining refrigerant. The lower the temperature in the liquid line, the greater the heat removal capacity. Greater subcooling can also be achieved by one system cooling another so that the system can more efficiently reach lower temperatures. This is known as a cascade systems. Cascade systems are usually required for ultra low temperature applications. So just to review, to measure subcooling, use your gauges. Convert the high side to a temperature. This should be the ambient temperature plus 30 to 35 degrees for most air-cooled systems. If you do not have that 30 to 35 degrees, do not go further. Your system is not charged properly, or there's another problem, dirt. Measure the condenser outlet or the liquid line temperature. Subtract the liquid line temperature from the condensing temperature. That difference is subcooling. So again, on this diagram here, okay, I have 95 degree ambient air. That's the air that's being pulled through the condenser. Notice I'm not taking it over the top of the condenser. I'm looking at the air that's being pulled into the condenser. This is R410A. My temperature, or the technician measured 390 psi G, that's gauge pressure, 390 psi. He converted that to temperature by using his temperature pressure chart. Okay, came out to 115 degrees. 115 degrees minus 95 is 30. He's in good shape there. The liquid line temperature is 110 degrees. His subcooling is 5 degrees. Now, I have a little bit of a problem with a 5-degree subcooling, but before I said it's right or wrong, I'd want to go back to the manufacturer's charts and take a look at what my system is supposed to be doing. Okay, low subcooling could be charge of the system not right, could be dirty condenser coils. Okay, but it has something to do with the outside unit. So condensers and subcooling, you guys got to understand the water-cooled condenser, the temperatures, and the pressures associated with that as well. 10 degrees hot, refrigerant temperature is 10 degrees higher, okay, than the outlet water temp, 3 gallons per minute per ton. Those are numbers you have to know. Air-cooled condenser, 30 to 35 degrees higher than ambient temperature. And subcooling normally is between 20 or 10 to 20. I have those seen it now on the newer systems a lot higher than that. And subcooling is used on the basis of how much refrigerant is in the condenser.